Hey physical science students, this is Dr. B and we're starting the Introduction to Ohm's Law and Circuits Remote Lab. This is designed to be done by you on your own. We did it in class, but I'll give you some hints and kind of walk you through it as we go through. First, you're going to need to open the sim Ohm's Law. It looks like this. We're basically going to experiment with different levels of voltage, current, and resistance. Basically, we can change the voltage and resistance here, and we're going to look at how that changes current. Current is the I here in the equation. This equation says volt equals current times resistance. The current you can read here, and the relative size of the current will be shown by I. If the current gets smaller, the I will get smaller, and this number will also get smaller in milliamps. The resistance here we can change as well, and the resistance you'll see as kind of how much gets in the path of electrons. You can think of it as like shopping during a super busy time, like when there are a lot of people in the store. You trying to navigate the store around a crowd, you go a lot slower and it's harder for you to get through than in a situation where there are not many other people in the store and you can cruise on right through. Electrons have kind of the same situation. If there's high resistance, see the big R here, they have a lot of things in their way and they don't travel through the wire or the material very well. If they have low resistance, they travel much more quickly. You could also think of it as like a traffic jam versus free-flowing traffic. So the first question is asking, as we change the value of the battery voltage, that's the V right here, how does this change the current through the circuit and the resistance of the resistor? If the current or resistance remain constant, why do you think it does? So basically it's saying mess with the V, don't mess with the R, and see what happens to the current. So let's put R in the middle and let's mess with the V. As you can see, as we add voltage, we're basically adding batteries here. And the current is 15.6 at this voltage of 7.6. So as I increase the voltage, the current went up. Let's see if I decrease the voltage. Well, if I decrease the voltage, the current goes down. So now you have the relationship between V and I, or voltage and current. It's a direct relationship. Current goes up, a voltage goes up, current goes up. Voltage goes down, current goes down. Resistance doesn't change. We're not messing by changing the voltage by adding more batteries. We're not changing this resistor here. We're not changing the material of the circuit. So that's why our resistance stays constant in this situation. Now for number 2, as we change the value of the resistor, that's R, how does this change the current? If the current or voltage remains constant, what do you think? Why do you think? So now we park V in the middle and we play with R. If we have high R, there's lots of stuff in the way of the electrons and they have a hard time traveling. And the current is pretty low. At a high resistance, 915 ohms, the current is 4.8, which is relatively low. If we turn down the resistance, look at that I, it's much bigger and that number is bigger as well. And here we have a lower resistance. So lower resistance, we have more current. It's easier for those electrons to travel. It's like the electrons are on the freeway and there's no traffic jams. They're just cruising along when we turn down the resistance. And so the current, the flow of traffic, is higher. If we create a traffic jam and put a lot of resistance on the freeway, the traffic does not flow smoothly and the current slows. The current is less. The voltage is not affected here. We are just changing this resistor here. We can think of it as changing out the resistor to have fewer or more ohms. it doesn't change the number of batteries. So if voltage is constant and we crank up resistance, the current goes down with greater resistance, which makes sense. Not as much traffic flows if you put more traffic jam in the way. If we turn resistance down, we make traffic flow more smoothly. We remove the traffic jam. The current goes up. And it doesn't affect voltage. It's not changing the amount of electromotive force in the system. It's not changing the number of batteries. So it's not affecting voltage. We're just playing with resistance. So use this understanding to make predictions about a circuit with light and batteries. Well, if we put more batteries in, we have more voltage, we'll probably have more current. And more current means brighter bulbs. If we put a resistor in, we can make the current go down. The bulbs will be dimmer, but it will make the batteries last longer because we're not pulling as many amps from the battery as quickly. If you had a headlamp, one of those flashlights you wear on your forehead, some of them have the ability to turn the light up and down so you can preserve batteries. If you only need a little light to read your book in the tent, you can turn the light way down to preserve batteries. Or if you're, trying to find your way in the dark down the trail, you can turn it on full strength, but then your batteries go very quickly. So describe 4 of your experiments with captured images from the simulation. Well, what you want to do here is play with and capture different aspects of voltage and resistance. So you could, for example, turn the resistance down, like here, take a screenshot of this, turn the resistance up, take a screenshot of this, put resistance kind of in the middle, have high voltage, have low voltage, take a picture of each of those, and those are great experiments to do. So let's demonstrate our understanding here. If we change the value of the battery voltage, what happens? Well, we kind of explored that before. We're looking particularly here at how does the current through this circuit change? And this time we have to be very specific. We have to answer, say, if we make the current go, if we increase the voltage, the current goes up, and we have to give some numbers. So I'm going to say at 0.5 volts, the current is 1.2 milliamps. So at 0.5 volts, the current is, it was 1.2 milliamps. Now, if I increase the voltage to 4.4, the current goes up to 10.7. So if I have 4.4 volts, the current is 10.7 milliamps. Change those to a different color. So that's my evidence. I can explain if I increase the current, or excuse me, if I increase the voltage, the current increases. This is basically if I have more EMF, which is electromotive force, then I can push more electrons, which is the current, through the circuit. And you should come up with your own numbers. Don't use mine. How does the resistance of the resistor change? Well, it doesn't change at all. We're not messing with the resistance. If we just change voltage, it does not affect the resistance for the situation. So I'll explain a little bit more. For the situation above, the resistance stayed. So I gave my answer. If we just change the voltage, it does not affect the resistance. Now I'm explaining my answer. For the situation above, the resistance stayed at 412 ohms the whole time. Just write ohms out. In both cases, which makes sense as we were not altering the path of the electrons. So you have to change something about the way the electrons flow to change the resistance. And if you're just putting in more or fewer batteries, then you're not going to change the resistance. If we change the resistance of the resistor, so we'll park voltage in the middle, we'll make the resistance go up and down. You can look at the numbers when you go up and down. You can look at 150 ohms versus 29.3 milliamps. You could write down 829 ohms versus 5.3 milliamps. And say something about voltage is not changing as we change the resistance because we're not changing the number of batteries. We're not changing the electromotive force. We're just changing how much interference is in the circuit, how we're changing the path the electrons take. And we're kind of putting more stuff, more resistance means more stuff or more traffic jam in the way of the electrons. We're not changing the battery because the volts don't change. If we're just altering resistance, voltage doesn't move, just current. So hopefully that gives you a good idea of how to answer number 6. Make sure that you put in something ohms versus, and you put your milliamps in here. And then you do that for a second situation to try to indicate how things are changing. Oops, I need a blank there. So that's the first part of the lab on the Ohm's law. Now we're going to go to a different PhET simulation. This is the circuit construction kit. It looks like this. I've already made a series circuit here, and we'll make some other circuits as well. So the learning goals here are to explore basic electricity relationships, explain basic electricity relationships in series and parallel circuits. So we're going to build some different types of circuits in this lab. We're going to use an ammeter and a voltmeter to take readings in the circuits. The ammeter and the voltmeter are over here. This is the voltmeter, this is the ammeter, they're to the right of the circuit construction area. You can also change the electrons. You can have kind of conventional arrows kind of showing the flow of the current. You can have values. You can turn those on and off, or you can measure them with your voltmeter versus, or you can also use your ammeter to figure out the actual current. So that's kind of how the simulation works. You have your parts to build your circuits over here on the left-hand side. And let's see what we need to do first here. First, we need to make some predictions. Consider the pictures of each of these circuits and then answer the questions below. From the circuits above, predict which bulb or bulbs will be the brightest. Why do you think? So based on what you know about parallel and series circuits, pick whether you think bulb 1, 2, 3, 4, 5, 6, or 7 will be the brightest. Or you could say like 5 and 6 or 3 and 4 are the brightest. You could pick a couple if you want. And tell me why you think that. Current is the flow of charge measured in coulombs per second or amps in a circuit. Describe how you think current will flow in the different types of circuits above. You can either make a good guess, or you're welcome to build these circuits. I've basically built circuit number 1 here, and we can, if we want to look at the direction of flow here, you can look at that. It goes into the light bulb, around, we can build some parallel circuits as well and investigate those. I'm gonna keep electron. I'm gonna turn some of these off and just show electrons to keep things simpler. You can turn on and off whatever you would like as you work on the simulation. So explore the intro screen. That's what we're on right now. Of the Circuit Construction Kit DC, that's direct current. Build a circuit that shows how to make a light bulb light up. Figure out how to measure the current and voltage. Insert an image of your circuit with the current and voltage being measured. Well, let's work on that together. So I've built a circuit here with 2 light bulbs. I can measure the current in the circuit anywhere but by pulling this little meter here. If I want to measure the voltage, I need to use 2 leads, and I can measure it across a light bulb. I can measure it across this light bulb. I can measure it across the battery. Anywhere there's resistance, there's going to be some current. There's going to be some voltage. If I just take it in the wire, I'm not going to find anything. So let's take it across the light bulb, and you could take a picture of something like this. Let's move the voltmeter a little bit closer. So something like this would be a great thing to screenshot to show that you know how to create a circuit to light up a couple bulbs, and you know how to measure amps and volts. Remember, amps are current, and you use this little meter to measure amps. And you measure the voltmeter, and you have to use 2 leads here to measure the volts. So imagine you're an engineer making a string of battery-powered holiday lights. If a bulb burns out, current cannot flow through that bulb any longer, like if the wire at the bulb has been cut. Figure out how to hook up 2 light bulbs and a battery so that when one bulb burns out or is disconnected, the other stays lit. So Christmas lights used to be in a series circuit. But when one of the bulbs burned out, you've got a situation like this. If one bulb burns out, everything's off. So what we need to do is put things in, we need a parallel circuit. And so I will build a parallel circuit for you, just to give you an idea of how to use it. How to use this construction set. So I'm gonna make that disappear. I'm gonna cut that. I'm gonna put it over in it to its own little world. I'm gonna cut that. Kind of give these. So I'm kind of gonna give both of these their own little circuit. I kind of like to think about this as my siblings. When you kind of live with your siblings and it's pretty intense, you're in a series circuit, and if somebody goes off, the whole house kind of goes off. I'm grabbing my parts and pieces of the circuit from here. If I want a wire, I just grab the wire and I plug it in here. And I'm going to grab another one and kind of make a square here. Grab another one. So it's just easier to see how this is parallel. So there's two different circuits here. You can go around the inside loop if you're an electron, or you can go around the outside loop. It's kind of also thinking it like you have a friend that lives on two different blocks. So you can go see this friend or this friend, and here's your house. If one friend, if the road to one friend gets cut off, you can go visit the other friend. If this gets cut off, you can go visit the other friend, and it all works out. So this is what's called a parallel circuit. Let's put this all back together again. It's two different circuits that are connected. There's two separate paths for each light bulb. So you can show something like I just did. You can unhook one of the bulbs like this. And you can show that this still works here, even though one of the bulbs is cut or broken or not working. And explain why you think it works. Why does having two different circuits for each bulb keep one lit when the other one isn't working? So here's number 11. Imagine you want to make sure your battery for your string of lights will last as long as possible. A battery will last longer if it powers a circuit with low current. How could you hook up a battery and two light bulbs so the least amount of current flows through the battery? Use the measurement tool in the simulation to check your design. Insert images to illustrate that your circuit works as expected. So let's go see. We've got our two. These are shining pretty bright. The currents, it's 0.9 here, it's 0.9 here, it's 1.8 here, it's 1.8 here. How could we slow that current down? I think we could grab a resistor let's see, does that slow the current down? Oh, it's 0.6 there, it's 0.3 there, it's 0.3, 0.3, so yeah, that slowed it down a lot. The bulbs are going to be dimmer, but that's okay if that's what we want. If we want dimmer bulbs, but we want our batteries to last longer, like we just want to we just need a little bit of light to read or cook if you're camping and you've got your headlamp turned down. You don't need to like see halfway across the campsite. You just need to see what's in front of you. So we could use this system in a headlamp, one of those flashlights you wear on your forehead, to turn down the light just to where we need it so we preserve our batteries and make them last as long as possible. And explain why you think that works. Remember a resistor here. We could turn on the labels here. That's a 10 ohm resistor. So we're slowing those electrons down, we're making them kind of take their time and wind through this resistor very slowly, and that keeps them that keeps the battery from burning out so quickly. We'll make another video for developing your understanding, part 2. Thanks for sticking with me. This is Dr. B signing off on part 1 of lab 3.1, Introductions to Circuits and Ohm's Law.